Welcome to Lesson 3 of the semester. The first calculation-intensive assignment is associated with these lessons, so make sure you understand all of the material and inputs shown in this lecture. In this lesson, we will look at fuel moisture, what affects it, and how to calculate it. Ultimately, fuel moisture has a big impact on fire activity and behavior. So let's get started. In this lesson, we'll discuss fuel moisture importance concepts, the moisture exchange in fuels, meteorological variables that impact fuel moistures, the difference between live and dead fuel moisture, and how to calculate fuel moisture. Fuel moisture affects every aspect of the combustion process from ignition, spread in intensity, to fuel consumption and smoke production. When there is sufficient moisture present in the fuel, it will not burn. This is called moisture of extinction. This concept will be included in fire behavior and fuel models. When fuel moisture is low, there is a higher probability for intense fires. One of the factors considered when an area declares a red flag warning is when atmospheric moisture, and thus corresponding fuel moisture, is extremely low. Other fuels-related concepts, such as available fuels, will depend heavily on moisture. Remember that in the first lecture, we discussed that available fuels are the fuels that can burn at a given point in time. How exactly is fuel moisture measured? Well, moisture content of fuel is most commonly measured as a percentage of the dry weight. More specifically, it is the mass of water in the fuel divided by the dry weight times 100 to produce a percentage. The amount of water in the fuel is determined by weighing the sample, drying the sample to remove the water, and then subtracting the mass, post-drying, from the dry mass to determine the mass of water in the sample. The amount of moisture changes with time depending on the fuel characteristics and atmospheric conditions. But in a nutshell, it is the amount of water in a fuel particle as a percentage of the mass of solids in that particle. As shown in this example, fuel moisture can be computed as a percentage of dry weight or volume. Take a minute to study the graphic of the idealized fuel moisture of Duff material. The moisture exchange process of dead wildland fuels is a complex process which can be characterized by evaporation from fuels and the addition of moisture absorbed from sources, saturation, including the ground, the air, and precipitation. The fiber saturation point is the amount of water that saturates the cells of the plant material. In dead plant material, this is normally around 30 to 35%. The additional water in the fuels is found in cracks, pores, and other intercellular spaces. In rotten wood, there are many more open spaces which can soak up water. In some cases, the water content of rotten dead material can be as high as 300%. Live fuel moisture is regulated by plant ecophysiology and is generally between 50% and 300%. Evaporation is the shift in states of a substance from a liquid or solid to a gas, which occurs when water molecules become fast enough to escape into the surrounding air. This is a cooling process as lower energy molecules are left behind. The process of evaporation depends on heat energy and vapor pressure, the latter of which is a function of temperature, wind, relative humidity, and other meteorological variables. As seen in the last slide, evaporation occurs when water molecules acquire a high rate of speed and escape into the air. When these molecules enter the air, they displace air molecules. This effect can be quantified as the vapor pressure, which is the amount of pressure contributed to the total atmosphere pressure by these water molecules. In the example, a typical column of air having a typical atmospheric pressure of 1013 millibars and gaseous composition is shown. Water vapor is 1% of the amount of air and therefore makes up 10.1 millibars of the column. This is the vapor pressure. Saturation vapor pressure is a measure of pressure of water vapor when it is equal to the pressure of water in its liquid phase. Rather, it is the pressure required of the air to reach saturation. It is solely a function of temperature as seen in the graph on the right. Now that we understand the concepts of vapor pressure and saturation vapor pressure, we can adequately define relative humidity. Relative humidity is the percentage of water vapor in air relative to the amount of water vapor the air can actually hold. If we assume there is a constant amount of water vapor present in the atmosphere, we can conclude from the relative humidity equation shown that as temperature rises, saturation vapor pressure will rise, and as such, relative humidity will decrease. Vapor pressure deficit is the measure of the difference between vapor pressure of a plant and the vapor pressure of the surrounding air. When the vapor pressure deficit is high, the plant will lose moisture faster. VPD has an inverse relationship with relative humidity as well. There are several meteorological factors which are important when considering the rate at which moisture will be evaporated from or added to wildland fuels: precipitation, wind, solar radiation, and air temperature. Each of these factors alters fuels differently, as seen in the slide. In addition to the meteorological factors listed previously, the arrangement, characteristics, and topography of fuels are also important factors affecting moisture content. For example, fuels found at higher elevations may experience cooler temperatures, while those located in valleys may experience warmer temperatures. Solar radiation and temperature largely control fuel moisture, so the aspect on which the fuels occur are a big factor. The graphic above, which is normally found in the NWCG Intermediate Wildland Fire Behavior course, is a great illustration of how weather differs on each aspect. Note that fuels on north-facing aspects typically experience the highest fuel moistures, while fuels on southern aspects experience the lowest fuel moistures. Take a moment to study the graphic and try to apply your knowledge later when you're out in the mountains. Climatic changes in precipitation and temperature affect fuel moisture content on longer scales. In the graphic above, you can see that fuel moisture content generally is at its highest during early spring due to winter snow and rainfall. At the end of the summer, when precipitation is lower, temperatures are higher, and fuels have had ample time to experience evaporation, fuel moisture is at its lowest. The drying of dead fuels is accomplished by evaporation. This process occurs in three states: first, the constant rate period, then a decreasing rate period, and finally a falling rate period. The constant rate period takes place the same way as any evaporation process from a free water source and occurs when the surrounding vapor pressure is less than saturation pressure. The rate at which evaporation occurs is proportional to this outward gradient. During the transition stage or decreasing rate period, the rate at which fuel moisture changes is highly variable. The variations in rate during this stage are caused by fuel and environmental factors that are difficult to evaluate and generalize. As the moisture removal process gets below the fiber saturation point, the bound water vapor pressure is reduced and the gradient declines. This decline slows the rate of drying. For additional water loss, one of two conditions must occur. Either the surrounding vapor pressure must be lower than the bound water vapor pressure, or the addition of heat must be applied to the fuel. This increases the temperature and therefore the bound water vapor pressure. Often we think of this final stage occurring right before combustion during the pyrolysis phase of a fire. The equilibrium moisture content, or EMC, is the moisture content a fuel would reach if exposed to constant external moisture level. In the graphic here, we can see the relationship EMC has with relative humidity. When the fuel is gaining moisture, absorbing, EMC increases as relative humidity also increases. One way to understand the relationship between a specific fuel and the EMC is to categorize fuels by the time it takes them to reach EMC. The time lag principle is based on the idea that it is the time required for a fuel element to lose 63% of the difference between initial moisture content and EMC with a constant temperature and relative humidity. Fuels are often categorized by time lag based on their diameter. However, we are actually using diameter as a substitute for the surface area to volume ratio of forest fuels. Time lag classes are defined as 0 to 0.25 inches, 0.25 to 1 inches, 1 to 3 inches, and over 3 inches and duff. We often refer to these as 1, 10, 100, and 1,000 hour fuels. Here are some examples of representative fuels for each of the primary time lag classifications. Note that 1,000 hour time lag fuels are often slash and heavy timber. Time lags make it easy for fire personnel to quickly estimate fuel moisture and fire danger. However, because size determination of fuels is subjective and similar sized fuels may have different characteristics that alter moisture content, time lags can be unrealistic. Anderson suggested alternate time lags for various fuel types. Later, Nelson used ponderosa pine dowels attached to remote weather stations to represent 10-hour fuels in an attempt to capture more subtle changes in moisture content. All plants are designed to hold water, meaning they are hygroscopic. This is true for both live and dead material. The xylem is the water transport mechanism of plants and can be seen in this electron microscope picture. Like dead fuel moisture, live fuel moisture content has a strong relationship with seasonal changes as the plant grows. These growing processes can be affected by precipitation events, cold temperatures, prolonged droughts, and other variables. Generally speaking, moisture content is highest in new foliage just after emergence. Then it declines quickly during leaf growth. This table shows the relationship between season and foliage moisture content. Notice that new foliage starts the growing season with a large moisture content and then approaches the moisture content of old foliage with the onset of fall. Evergreen fuels experience seasonal growth cycles. New leaves will often have upwards of 250% moisture content, but then drop to 150% by midsummer and finally decrease to typical dormancy values in the fall. matching older foliage. Grassy fuels are very sensitive to short-term weather changes and longer seasonal conditions like drought or frequent rains. Annual grasses are more sensitive than perennials due to their limited growing season. Additionally, the curing time of these grasses can be altered by factors like rainfall and variations in solar radiation, temperature, and relative humidity. In this example of typical fuel moisture content in grassy fuels, you can see that during green-up in the early spring, moisture content can be up to 300%. As the growing season progresses into late spring and early summer, mature grass fuels can be expected to be around 100% moisture content. Later, when the grasses are completely cured, fuel moisture may only be about 30%. Fuel moisture can be estimated in several ways ranging from cheap and approximate to very expensive and precise. The first method is to estimate moisture content by volume. This method measures the percent of water content of a known volume of fuel. The process consists of measuring the fuel volume while wet, drying the sample, and measuring the volume once dry. Once the sample is dry, you subtract the dry volume from the wet volume to get the moisture volume. Then divide the original volume. The result is the percentage of the original volume that was made up of water. The advantage of this method is that you can incorporate different fuels for better estimates at the stand or site scale. The next method is to use gravimetry. This method measures the percent water content of a known weight of fuel. The method used are similar to that of volumetric method. However, this method is more advantageous because of ease of sampling and a low cost. This is the most popular method and is often conducted for different classes of fuels. Another popular method is to use moisture indicator sticks. These sticks are 1/4 inch diameter by 20 inches long and are made up from pine. They are placed on brackets 10 inches above the litter layer. These sticks measure the moisture on a standard scale and apply as a site average. Their big advantage is that they are site-specific and do not require a drying oven. However, the disadvantage is that they only predict 10-hour fuel moistures. The other time lags must be assumed. Another, less obvious method is to simply use an ocular estimate. This process includes the observation of color and oftentimes extensive previous knowledge. This method includes touching, feeling, and breaking fuels. This can require extensive field experience, but is a very cheap method. A newer version of ocular methods is performed by using remote sensing. An example of this in the United States is the AVHRR, Normalized Difference Vegetation Index, which shows vegetation greenness at a 1.1 kilometer resolution. More information can be found here. The most precise method of calculating fuel moisture is solvent distillation. In this method, you place a sample of fuel in a sealed container where it is volatilized. The vapors released during volatilization are collected and cooled. They are then weighed. This is a very precise but also costly and laborious method. One other method that is becoming popular is to use instruments to measure moisture. This method uses electric resistance probes to determine woody fuel moisture content. The major advantages include portability and precise measurements. However, the applicability of these instruments has a limited range of moistures and they can be difficult to use on small fuels.